Hello, everyone, and welcome. I'm David Pointing from the Australian Power Institute, and welcome to our fourth webinar in our Innovation Project series on electric vehicle integration. Today, again, you'll be hearing from our expert research team at the University of Melbourne, but also from my colleague James Seymour at C4Net, or the Centre for New Energy Technologies. So a quick bit of housekeeping first. We are recording this webinar as we have done with the previous three. So that will be available after the session today, a couple of days, and the previous three webinars are also available through the API's YouTube channel or through C4Net's project website, which I'll have the link up for in a moment. As we come together with over 400 people registered for this webinar all across Australia and in fact around the world, I'd like to acknowledge the traditional custodians of the lands and waters upon which we are meeting today, and to pay my respects to their elders past, present and emerging. I'm here in La Truita or Tasmania, and I welcome those of you who are all across Australia, and just point out that this handy map on the screen is a good way of finding out what the local cultural connections may be for where you are. So our fourth webinar today is focusing on the initial findings of some of our projects. And as I said, the three previous webinars and the slides are all available for you on C4Net's website and also the Melbourne University team's website. Just a bit of background. So I'm from the Australian Power Institute. Our role in this was in bringing university teams together with industry and in disseminating that information. So hello and thank you to any of you from our member organisations out there. We very much appreciate your support. And it's lovely to work with Energy Networks Australia on our what's called the ASTP, or the Australian Strategic Technology Projects portfolio, where we do this across a number of different projects, all driven by the specific needs and priorities of the ENA's members, supported by the API's members. And with particular projects such as this one, we love working with other partners such as C4Net. So these projects are funded with $200,000 over 2 years. So they're constrained to 2-year projects funded by ENA, and through a competitive process, we identify the best university teams to work with and bring together that industry expertise and need and that rich university talent that we have in our Australian institutions, and deliver outcomes for industry. But I'll just pass over to James now from C4Net, who will talk a bit about their contribution and their interest and passion for this project. Over to you, James.
Thanks a lot. Thank you, David. And it's great to have the Melbourne Uni team here and I'm really looking forward to hearing what they've got to update us on for this webinar. I come to you from Wurundjeri Woiwurrung people country, the traditional owners of this area, and I also pay my respects to their elders past, present and emerging. We're really pleased to join with the ASTP program here, the Australian Power Institute and Energy Networks Australia, and likewise we've made a financial contribution, as have the Victorian government, to this project. But I'd also like to recognise all the distribution members who not only have provided the data to support this project, and that's both members of C4Net or from Energy Networks Australia, but have provided a lot of the guidance and everything. We as a team, we meet quite regularly with the researchers, providing feedback and working through some of the issues that are there. And it's a very collaborative project. It's one that we really enjoy from that aspect. And that's really goes to C4Net area, because we're into the applied research projects and committed to maximising the data to support those research efforts, and also the development of evidence-based policy formation. To do so together with our DNSP members, AusNet Services, Gemina, City Power, Powercore, and United Energy, and with support from the Victorian Government, we've actually launched a data access service, which is to help all researchers access electricity data from the 60% of smart meters, of Australian smart meters that actually sit here in Victoria. Judging by the response to date, it appears there's a real appetite for that electricity data to inform how to address customer needs, engagement, power system challenges, network hosting, the uptake of solar batteries and EVs and social challenges. So please, if you have any needs for energy data, please do be in touch with us through data@c4net.com.au. And specifically for the EV area and the electrification of transport being such a key element of our energy future. But we're well aware that a barrier to good research at the moment is finding good quality, well-curated data to support that research and inform that transition. And so we are building a data warehouse, an EV data warehouse. And again, this is a great opportunity to not only contribute data sets, but also to enhance knowledge sharing and promote insights from your work. And so please be in touch with us through data@c4net.com.au if we can help in any way there, or you'd like to contribute or guide us to data. So look, throughout this session, please make the most of that chat function to post questions. We really want to try and encourage this to be engaging. We love it that so many people have responded to this webinar, and we really look forward to your comments and bring the challenges alive. But with that, I'd really like to hand over to the team from University of Melbourne.
Thank you very much, James. Thank you very much, David, as well. Welcome, everyone. Let me start sharing my screen here, and let's start. So in the next 40 minutes or so, we're going to have two parts here for this webinar. The first part is what we've been advertising, the initial findings on the management of electric vehicles that we have done, and we'll be finishing the next month or so on Australian urban and rural grids. But we have a second part that is as interesting. It's part of a report that was delivered already late last year, and now we want to disseminate as well some of the key findings. It's really a survey about EV charging consumer aspects, and these insights are very, very valuable. So we will spend more or less around 20 minutes in each part, and we will start. Patricia will be delivering the second part, and she's with us as well today. The first part will be delivered by myself. I'm Nando Chua, a professor at the University of Melbourne, and Dr. Wilnack Manson. Some of you that have already been in this webinars already know us, I guess. So what I'm going to try to do in the next few minutes is to really give you a structure where you will understand a little bit of the project and what we're trying to do as well at this stage. And then we're going to get a little bit more into this management of electric vehicles, particularly what we call the EV charging point management. There are many strategies. I'm going to discuss briefly, what things can be done, to manage electric vehicles as such a charge, excuse me, the pun word. But we're tackling this analysis just with one strategy. There are multiple strategies. And we will finish with some key remarks and next steps as well. And we'll have Will as well producing some interesting results for us there. So first, the project. You already heard about the project, the funding that comes from ENA, API, and C4Net. So just to let you know, right now we're in the more or less, but we're in the second half of the project, but we're finishing the third sort of milestone, which is distribution network integration of electric vehicles using active management strategy, which is really what happens to our distribution networks the moment that we start using active management. And this is really related to the management of electric vehicles. Our report will be delivered in March. So we're talking about next month. So that's why we're providing some of the initial findings at this stage. But then it moves on to techno-economic analysis as well that you will hear in the next coming months to the end, that is September this year. This is the team. We have different people with the techno-economic parts, but also with transport and, of course, customer aspects. Moving on, let's get into the context of electric vehicles and the grid. So I normally present this slide, and I think it's important just for us, all of us, to remember all the time, what are the challenges that we're talking with electric vehicles? Well, we always need to remember that the design of the electricity grid, and particularly the grid that is connecting our homes, to which we're going to connect our electric vehicles, charging stations as well. It has been designed thinking of what we call an after diversity maximum, which is like an average peak demand, that we already estimated, for different type of houses in different regions. And everything works well, of course, because it has been designed having in mind that typical demand. However, of course, this demand varies across regions, demographics, etc., etc. So you can see there in the table different values of A, D, and D. So these are KVAs that varies in New South Wales, Victoria, and Tassie, and that's okay. All right, there's nothing wrong with that. We design our networks considering the local characteristics of our consumers. Now, that means that perhaps then if we design them, with those values, and normally we over-engineer things, all right, which is nothing wrong because we prepare for the future a little bit. You can argue, well, surely there's a lot of space for electric vehicles. Well, there is room, but not necessarily so much. So let's talk about electric vehicles. So at this stage, many people that already have electric vehicles might have what we call here a level 1 type of charging, which is 16 amps, which using the local voltages, we're talking about 3.7 kilowatts. But more and more people will be installing the 7.4 kilowatt level 2 chargers, which is really the trend around the world. Now, those values really are quite high. And the moment that we really have a significant conscience of all these people coming back from work with connecting the electric vehicles, well, you might have a very large increase in the peak demand. And that can be, of course, a matter of concern for the companies that manage the poles and wires, right? But to what extent is this a concern? So we need to quantify things. And that's the whole point of understanding the hosting capacity of networks and their ability to host this particular technology. Now, this is not just the poles and wires that connect our homes. Of course, those poles and wires are connected to more poles and wires, which are the high voltage networks, as they are known here in Australia, 22 kV line-to-line networks or 11 kV. And they are different depending on the characteristics, the rural areas or the urban areas or whatever it is in between as well. However, the more we have electric vehicles, the more we are going to see the corresponding problems due to the increasing demand. Now, the first question, of course, that we already try to answer with our reports and webinars is how to determine the EV hosting capacity for networks. We have done extensive modeling. All the results are in webinars and reports, so I'm not going to go into the details of that. We have already done it. And the results really, I'm going to do a quick recap later, but suggest that we need to do something about this, or if we don't do anything clever, we're going to end up with the traditional sort of way of managing our problems, which is more copper on the ground. So larger conductors, larger transformers. And that, technically speaking, solves the problem, but that means a lot of money as well. And that is not necessarily the best solution, right? So the second question is then, how can we increase that EV hosting capacity? Hopefully without really more copper on the ground, right? So before we get into more things, just very quick definitions. EV hosting capacity, when I mention this, is the amount of electric vehicles that a given distribution network can host without negatively affecting its normal operation. What is normal operation? It can have many parameters that are important for electrical networks, but we're going to focus on voltages as the voltages that you see at the connection point of your house, and asset utilization. So you don't want conductors and transformers to blow up, simple as that. And when I say amount of electric vehicles, it's really related to the number or percentage, particularly, of houses with a single electric vehicle. So 100% of houses means each house has an electric vehicle. Some of you might think, well, some houses can have 2 electric vehicles. That's true. And then we will go beyond 100%. But now let's reflect on the potential solutions that we might have to increase electric vehicle hosting capacity. As I mentioned earlier, well, we can use our traditional approaches, which is the one there that says with new assets, reinforcements, okay? But let's look at other options. We can use to manage voltages our offload tap changers. the distribution transformers. In Australia, it's very common to have that. We just change that position. We have to disconnect the transformer, and then we have better voltages. Or we can do that as well with our primary substations, or known here in Australia as zone substations. But that is just voltages, right? The advantage, however, is that it is not that expensive to do that, but it's only voltages. What about with asset congestion? Now, if we look at new assets and we look at reinforcements, of course, you will sort out all the problems related to congestion because you have larger cross sections, so you can have more flows of power. But reinforcements do not necessarily solve with voltages, sort of voltage issues, and the price tag can be quite significant. What about regulating voltages, with new type of transformers closer to end customers? Well, that's fine, but that is only voltages, not currents, and that can have as well a very big price tag. And we have already done this for photovoltaics in another project, and we can share the links later on, but that can be quite expensive as well. So that is why we have this direct or indirect management of electric vehicles, which can solve both voltage and thermal problems, and perhaps the price tag is not that big. Right? So management of EVs might be a good option, but to what extent, and what about EV users? The moment that we manage electric vehicles, it means that the charging that people were going to or expecting might change, right? So what do I mean by this management, direct or indirect? So when we start managing electric vehicles, it means that we're gonna see less demand because we're doing something clever to manage that demand, right? And that means that technically speaking, we might solve other problems related to voltages and asset congestion. All right, fine. So what do we do then? Let's get a little bit more granular there. So you can have a direct management or indirect management. The direct management can be the distribution company or a third party that will disconnect the charging points. Really, when there are problems in the network, you will need to sense a problem. You could also do throttling, which is essentially instead of your 7.4 kilowatts, just 7 or 6.8. That, however, has challenges. Not all electric vehicles are able to do that, or not all the charging points are able to do that. You can schedule the charging as well, and that's great. But again, not all charging points can do that necessarily, or electric vehicles. You can do indirect management. You can use time of use tariff as well. And we will be exploring in this particular project the disconnection of charging points and the time of use tariff. But for the findings today, we're going to focus on the disconnection of charging points. So let's get into the disconnection of charging points, or EV charging point management. Now, just as a recap of all the project, of everything that we have done, so we have 6 networks fully modeled down to the end customer. I mean, the low voltage part actually was using some techniques that we call pseudo low voltage feeders, so very realistic, but not the real ones. And we're going to do all the analysis in all these networks. But today we're going to present only for Hazelbrook, which is a rural New South Wales feeder. Now, another recap, and this table is the EV hosting capacity without any management. And what you can see is that in red, there's a problem, all right? What type of problem is what you see, the V with voltage, or the transformers, or the conductors, etc. Now, a lot of red, right? And that's not great. That means that many networks cannot really have significant volumes or significant numbers of electric vehicles. So we need to mitigate these problems, this asset congestion and voltage drop. And this has to be done per transformer, per LV feeder, per phase, per customer. And this is challenging because what can we do, to really do this well from a technical perspective? So when we talk about this EV charging point management philosophy and the strategy that we are assessing in this particular project, we are considering from simulations. So this is not a trial. Yes, from simulations, although it's based on a trial that was done in the UK a few years ago. We are assuming there are sensors at the head of the low voltage feeders, which is not common. So for the currents, we are assuming that we cannot connect to the cars to know the state of charge. So we're going to connect only to the charging points. So that means that there's no issues with communications with the actual car, it's just with the charging point. So it's like disconnecting a plug if you want. And then we will have sensors at the charging points as well, and the corresponding actuator to disconnect it, all right? And all of this will receive information from a centralized controller that will be looking at all the LV feeders in a given high voltage feeder. So we're looking at dozens, hundreds, or thousands of LV feeders. And the idea is to manage voltages and the currents that are going through the feeders and the transformers. Now, technically speaking, if it is very well put together, this idea, yes, you can sort out all the technical problems, all right? And this is all good because it will be with relatively limited infrastructure and non-network models, which is also very important for distribution companies. So this is what we are analyzing in this project, and one of the things that we're analyzing, and we're going to share with you some of the findings. Now, just for you to understand a little bit more the philosophy, well, we need to check voltages, conductor utilization, transformer utilization, and when we see a problem, we disconnect the electric vehicles and we reconnect the electric vehicles when there's no problem. Which vehicles you connect or disconnect? Well, it will all be based on the length of connection. So we will have a timer once an electric vehicle is connected at home, and that timer will be used to create a ranking, right? Now, what will happen with electric vehicles? So what you see here is a schematic of what will happen. What you see in blue is a profile without electric vehicle management, which is saying, well, this particular vehicle will actually be charging at, I don't know, 6 p.m. to 7 p.m. And then later it will be charging at 11 p.m. to 2 a.m. All right, so that would be the normal profile without any management. With management, because there are many other vehicles doing similar times of charging, this vehicle will be pushed to later. So essentially, the EV management will push vehicles that are creating a significant coincident peak demand, and then will push them to charge later. Now, of course, what you can very quickly say is, all right, so that's interesting, but how much are we affecting these EV users? And that is a very crucial part of this analysis. We don't want only to say we have a solution for the networks, we also want to understand what are the effects on EV users, because that will really be the tipping point to which you can say, well, we cannot do more EV management if everyone has electric vehicles because the delays are just way too big. Now, at this point, I invite Will to continue. Will?
Yes, thank you, Nando. So as Nando's pointed out, without EV management, we can get significant congestion issues and voltage drop issues. And if we look at the graph on the right, we're showing here the net demand of the whole HV feeder, Hazelbrook, the rural New South Wales feeder. So with EV management, we're looking to disconnect those charging points, cut the problem off sort of at the head, if you like, with the objective to manage the transformer congestion, manage the voltage issues, and ultimately through doing that, we'll lower that peak demand. So what we can see here is 60% EV penetration as an example. In the blue line, we see the normal unmanaged demand when we consider unmanaged EVs. And when we consider the management, we can see that effect Nando was just talking about of taking that profile during that problematic period and shifting it to a time where there is capacity. So if you look at the green line, you can see that during those peak hours, around sort of 7 to 9 o'clock, there's a significant drop in that aggregated power across the whole HV feeder. And then we shift that demand into the lower demand periods during the night. And then by the morning, the plots join up again where any delays that did exist have been resolved, and we now match up with the natural demand of the network. So the real takeaway here is with EV management, we're trying to solve the issue. Through solving the issue, we're reducing that peak demand and charging when there's capacity in the network. So if we move to the next slide, we can see here, this is the transformer utilization, the LV transformer utilization of every LV transformer within the HV feeder. The second plot is the customer voltage. So this is every single customer, residential customer, and their voltage, regardless of if they have an EV or not, because ultimately all customers will be impacted by a bad voltage. And finally, the LV feeder utilization of the conductors within those LV feeders. Now, the main takeaway message here is without the management, we have problems in the transformer going too high in its loading, and we have voltage drop issues. And when we have the EV management and we shift that demand to times where there's more capacity, we're able to manage the LV transformer utilization, we're able to manage customer voltages, and the LV feeder utilization in this case still has no issues. So with EV management, we solve those issues. So if we move to the next slide, please. So what's the impact on customers? So we're able to solve the issues, but what's the impact on customers? On the left here, we're showing what we call is the customer impact level. So we take the charging time without, with management, We divide it by the original and we get a ratio. Now, if there is no delay at all, we just assign it 0. So we don't mix things up, and then we round it. So if there's a charging increase of 1 to 1.5, that's 1, and then 1.5 to 2.52, so on and so forth. So it's a ratio of the increase in charging time. And then on the other side, we can see the distribution of charging times with and without management. So in blue on the right there, on the right graph, we can see that 75% of the customers have a charging time between sort of 2 to 4 hours, and that slightly does increase when we have management. And there's a slight uptick in the sort of upper quartiles. But what we can see with the CIL, and we can also see with the box plot, is that most EV users are not affected. Over 80% don't have any effect at all. It's as if they're unmanaged. And those that are delayed, the longer charging happens at night when they're asleep. So the likelihood is these delays will resolve themselves before the morning. We did see that to some extent with the net demand graph. So there are delays. Most EV users are not affected, and most of the delays do happen at night. So the question is, is that okay or not? And is that worth the offset of deferring reinforcement that is expensive? So if we move to the next slide, please. We can see here the effects of this management by managing our net demand, by solving those network issues on the net demand. So what we can see here is, yes, as we increase in EV penetration, that blue line without management increases, so the problem gets more and more severe. And we can see with the green line, the EV management is managing those network issues, keeping that peak within what it deems appropriate for each LV feeder, and then aggregated over the HV feeder, and we solve those issues. And we can also see that, those peak hours from 7 to 10 are moved into those lower demand periods. And as we increase in EV penetration, that shifting sort of increases in its magnitude. So at 100%, we have quite a significant amount of charging between midnight and 4 a.m., whereas before, there was very little. And finally, if we move to the next slide, we can see an overview of the impact on customers. We can see that, yes, at 20%, almost everyone is unaffected. There are a few people affected, but very few. And as we increase in penetration here at the top, we can see that the number of customers that are impacted as a percentage of the total number of customers, that's decreasing. So as we increase in penetration, 20, 40, 60, that green bar is slowly going down as more and more customers are increasingly required to delay their charging in some way or manner. Now we can see that most of the charging is between sort of 1 and 3. So that ratio of the charging time. And if we look at the profiles at the bottom, we can see that there is an uptick in the time it takes to charge an EV, but certainly between 20 to 80%, it's not too different from what was already there, but there is definitely an increase in charging time. So the question here is, we have more EVs when we have management, with more EVs, we affect the EV users more. So the higher we have a penetration, the more and more customers are going to be impacted from management. So the question really is, what point do you draw the line as acceptable before you then start necessitating reinforcement at a cost? So where do these delays are acceptable or not? But that's for people to conclude themselves. So I think this is where I now hand it back to Nando. Thank you.
Thanks, Will. So let's go into the key remarks and next steps. At this stage, there might be many questions. We are gonna go through the questions, of course, through the chat. So please just write your questions in the chat. So let me just give you some key remarks here on this part 1 of this webinar. So definitely EV management will bring many opportunities, right? As you can see, technically speaking, if you disconnect the excess load that we're calling excess, the electric vehicles, this excess because the networks were not designed for it, right? So if we disconnect it, of course, the problem goes away. That's pretty obvious. And technically speaking, well, as we are showing with the simulations, yes, the problem goes away. You need to be a little bit clever with the management strategy, etc. We didn't provide all the details today, but that could be done. This is something that could be done today with the technology that we have. Sensors here and there, communications, and the controllability of charging points at home. But all these opportunities come with challenges as well. So on the positive side, yes, can we actually implement this tomorrow? Well, yes, technically speaking, yes, if we want to, all right? Because techniques like this are based on rules. They don't require so much information. Yes, you need some sensoring, of course, that is not that complex, but as it's not that simple, but it's totally doable. And it's scalable because you can do this across massive regions. It mitigates all network issues. That is fantastic. But of course, there's new infrastructure requirements, there's cost, and also the fact that EV users will face longer charging periods. Now, that is a negative, but at the same time, I don't want to just highlight it as a negative, because at the end of the day, it's all relative. And well, if you were planning to charge a vehicle for 3 hours and then now it's a 3 hour and a half or 4 hours, but you're sleeping anyways, is that something that you really care about? And that's why you need to stay, tuned with part 2, which is where we're going to hear from Patricia, the fact that actually people might not mind to have that sort of management from a third party, all right? Now, what is this tipping point for EV management? Something that I mentioned earlier, Will was highlighting as well. So it's not that we're going to give the answer here, because at the end of the day, what we're trying to do for the final report and what you're going to see in the final webinar of this part of the study is that there will be a trade-off between user acceptance or the impacts on EV users and network augmentation. And that's for the decision makers to decide. All right, that's what they're called, decision makers. And it is quite tricky, because we need to understand to what extent you or us as a society are happy to affect a tiny amount of EV users, just to avoid all this extremely costly process of augmenting the network. Or perhaps we might create some solutions that are super localized just for those EV users that are really heavily impacted, but the rest is okay. So there are different things that can be done. But what it is important, from these initial findings, and it is just one network, the rural New South Wales, is that the very high penetrations, users are, large majority are unaffected. So this is where I stop. Just to mention that the next steps include, of course, extending the analysis that you have seen for all the other networks that we have. That's going to be very exciting as well, because they are extremely different. We're going to apply time of use tariffs as well, not as the tariff itself, as in dollars, but kind of highlighting hours, periods of the day where there will be an increase in tariff, and then therefore there's an expectation of some EV users to shift their demand. Now, we're going to do a sensitivity analysis, because really the reality is that we don't know what is the proportion that is going to be really shifting their demand. But still, that analysis is interesting to know to what extent, or what is kind of that trade-off, proportion of people with a given time of use tariff that might bring network benefits, meaning non-network impacts. And we will produce the report and the webinar for March and April coming. I'm going to just skip this slide because we are going to share the slides with you. I just want to thank all the DNSPs and Jing as well that has contributed to this. And we move on to the second part of this webinar. And Patricia, I'm going to stop sharing my screen.
All right. Good afternoon, everyone. Let me share mine. Oh, good. Can you see my screen? Yes,
we can.
Good. Yes. All right. So yeah, hi everyone. Thanks for having me. I see a lot of questions in the chat, so I'll try to be quick so that we have enough time at the end for the discussion. So I worked in an initial part of the EV integration project in which we focused on consumer behavior. I noticed in the field, it's used a lot the term customer. If you're gonna see throughout my presentation, I end up using the word consumer. In this part of the project, we started off with a comprehensive national and international literature review. And then we conducted a survey with Australian consumers. So in the second half of the webinar, I will share some of the findings from the survey. The survey had an exploratory scope and aimed at generating insights about charging preferences of Australian consumers, as there is, as we noted in the literature review, there is a scarcity in national empirical data in this sense. The survey had three main objectives. One was to have some idea and characterize a little bit EV ownership and consumer general purchase intention. And then the second objective was to identify the preferred locations and times for EV charging among current owners as well as potential owners. And then finally, we aim to understand consumer willingness to adopt time of use tariffs and supplier managed smart charging systems in an EV charging scenario. I'll start off with some details about the sample. So considering the low incidence of EV ownership in Australia, we couldn't really rely on a random sample of vehicle owners to investigate both EV owners and non-owners. So we decided to segment the sample. So we collected data from 1,000 respondents, and sample one targeted at 900 responses from drivers of regular vehicles, of internal combustion engine vehicles. So you're gonna see, I use the acronym ICEV throughout the presentation, while sample two aimed to reach 100 EV drivers. You can see that the final numbers are slightly different, who are considered still early adopters of this technology. So these consumers, they do not represent what's going to be the behavior of the mainstream consumer later on when EVs becomes more disseminated, but they bring some interesting initial perspectives. You may notice that we are actually focusing not only on owners, but specifically on drivers. And drivers were defined as individuals who are 18 years or older and hold a valid driver's license and live in a household that owns at least one car. So here is an important point, because when I talk about the sample of EV owners or EV drivers, they are actual drivers. They are, if the household owns multiple vehicles, this is the person who drives the electric vehicle. So they are very familiar with the technology. We delayed the data collection a couple of times to try to avoid COVID-related restrictions and lockdowns, but that was not possible. So this data was collected in July and August last year, and it was affected by some COVID restrictions, especially in terms of some travel and parking patterns that we measured. So that's why this is not the focus of the presentation. The results that I bring are more general. For the sample of ICEV drivers, we did apply quotas and weights to make sure that that sample is representative of the population of Australian drivers in terms of age, gender, and gross household income. The sample of EV owners, we don't really know what is the social demographic of this population. So we couldn't do anything about it. So it's more of an exploratory nature. Okay, so let's start by examining what we observed regarding EV ownership and purchase intention. So first, looking at our sample of EV owners and the type of vehicles that they own. If you look here on the left, it's a graph that I borrowed from the Electric Vehicle Council, which shows the sales of EVs in Australia. You can notice that the sales of plug-in electric vehicles is more than 5 times higher than that of plug-in hybrid electric vehicles since 2019. However, in our sample, we see that the distribution is almost half and half. which is an indication that our sample is not representative in terms of vehicle type, but it's still, it gives us a good behavioral understanding. In terms of the plug-in electric vehicles, we see that the majority of the sample owns Teslas, which seems to have been observed by other researchers in Australia as well. So Tesla seems to be the most popular make. In terms of geographic distribution, we saw here, I don't have information on the slide itself, but just to let you know, we saw an overrepresentation of respondents from New South Wales, both for EV owners and non-EV owners. So both samples had this overrepresentation, but for the remainder of the states, we saw some similar trends to what we see in terms of vehicle registration distributions. We observed that for EV owners, the majority are located, more than 83% were located in the main metropolitan areas of the states. While for ICV sample, this number is lower. We have only 68% located in the main metropolitan areas. So as I mentioned earlier, the ICV driver sample is representative of the Australian driving age population in terms of age, gender, and gross annual income. However, here we can compare that with the EV driver sample, and we see that EV drivers show higher shares of men, individuals between 35 and 44 years old. Also, individuals who have higher levels of education, at least a bachelor's degree, and those who are employed full-time, as well as individuals in the high income bracket. You can see that the majority, the high majority of the sample of EV drivers is in the bracket above $100,000 per year. In terms of travel patterns or amounts of distances traveled, in 2020, passenger vehicles in Australia traveled on average 11.1 thousand kilometers. Our ICV sample shows an average that is lower than that, so that they are a little bit below national averages, while the EV driver sample is way above that. It's pretty much 2 times, so 20,000 kilometers a year. So 2 times the national average, showing, and this is usually associated when you look more carefully inside some other variables, you notice that that is usually associated with once most people are full-time employed and they also have longer commute distances than average. So these people are driving a lot to and from work, which is an interesting thing to think about. And it's also expected that people who drive longer distances, they are willing to spend more money to purchase cars and to have more comfort in their commutes, right? But it's interesting to notice that this is a pattern of this is a behavioral aspect of early adopters, right? Early adopters do drive longer distances than national averages. So, I mean, I think once you see that adoption will grow, you perhaps will expect a decrease in demand or a decrease in the amount of charge that is necessary per vehicle if people keep the same travel patterns that they have nowadays. In terms of intention to purchase an EV for for those who are currently ICV drivers, we observed that close to 36% of the sample don't see themselves purchasing an EV in the next 10 years, which shows that perhaps something needs to be done in order to increase the acceptance of these vehicles among the mainstream consumer. We also observed that our sample is probably has a high representation of EV enthusiasts, as we see that 12% of the sample seems to be already doing some research in order to buy an EV or plans to buy an EV in the next year. So now moving on to charging perceptions and preferences. So the reminder of this presentation is organized as a comparison between current EV drivers and potential consumers. And we are comparing them in terms of their perceived ability to charge an EV at home, the perceived ability to charge an EV at work, as well as their charging management preferences. It's important to notice why these comparisons, and that's because charging preferences of current EV owners may differ from those potential consumers simply because of the difference in experience using the technology, but also in terms of differences in social demographic characteristics, as we mentioned earlier, and differences in personality traits and lifestyle preferences. So while EV owners answer their questions based on their current experience, non-ICV drivers answer the questions based on hypothetical scenario that was the ownership of a plug-in electric car. They should imagine that they had parking arrangements that allowed for them to charge the vehicle in their houses. And we also provided some usual charging rates available at different locations. So in terms of the ability to charge an EV at home, we observed that even though charging facilities parking availability in people's houses are similar, the distribution for EV drivers and ICV drivers do not vary too much. When we ask them whether they believe they are able to charge a vehicle in their house, we see that the great majority of EV drivers is able to charge a vehicle in their houses, while the mainstream consumer perhaps do not have the same perception. So only 50% of the respondents believe that they would be able to charge the vehicle in their houses, which is indicating that they are probably underestimating their ability to charge in their house. We observe a similar pattern for ability to charge an EV at work. We see many, around 90% of the EV drivers who drive to work say that they are able to charge a vehicle around their workplace, while the ICV drivers, around 76% believe that there is not the possibility of doing that, or they are not familiar with parking spaces that offer this possibility. For EV drivers, we observe that the options that are available to most of them are standard chargers, so not fast chargers, and that can be either paid or free. Oh, time is flying. Here is interesting to see that 61% of people say that they have level 2 of charging, which there may have been even some misunderstanding in this question, or I'm not very confident about this number that we observed, especially when we see that only 52% of the sample has plug-in electric vehicles. But nevertheless, it seems to be a trend to start installing level 2 chargers. We also observed that having solar panels and adopting time of use or EV specific tariffs is more prevalent among EV drivers than ICE EV drivers. Here, in terms of their preferred charging times to start charging their vehicles, we observe very similar patterns between EV drivers and ICE EV drivers. EV drivers are reporting on their actual usual start time, while ICE EV drivers are reporting on their preferred start time. And it's very similar, with peaks coinciding with our evening peaks, which is not very good news, especially after we just saw in Nando's presentation. On the other hand, some good news in terms of time of use tariffs are that people are willing to change their start charging time based on discounts. And as a summary, at a 50% discount level, we would see 42% of consumers would move either to the midday time, where you have excess of solar, or to after 11 p.m., while 33% would only move to the night of peak time, and 8% would only move to the midday time, which again, those are some promising results in terms of managing using time of use tariffs. Some people may ask, well, we already have some tariffs that reflect this type of discount, and that's not necessarily what we observe. And this is something that we should discuss in the future, because it's really consumers need to be become more aware of how to select those plans and so forth. I really want to move on to our last bit of the presentation, and that's where we asked people about what Nando was talking about. So how would people feel about accepting supplier managed charging, so direct load control? And so we asked people what would they prefer. They would prefer to do unmanaged conventional charging, so they select their own times to charge, or they would prefer a system that the residential charger controls the load based on a price signal that is dynamic. So there is no direct control from the supplier, but there is some management happening through price signals, or they would accept the supplier controls to the load. And we observe that the acceptance of supplier managed charging is a lot higher among current EV drivers than it is among ICE EV drivers, which calls for some campaigns, I would say, or some educational campaigns, or either providing people with a better understanding of what that takes and how that really impacts the charging. Because just by telling people that they will lose the control, or the supplier will be influencing on how long their vehicles take to charge, it's probably not the best way to have it being accepted by users. I will really, well, we also mentioned the ability for users to use apps to override the supplier management, and that does seem to improve the acceptance among mainstream consumers. I really will just, I guess I have mentioned already most of the main takeaways here, so I will just cut myself short because I'm going already over time so that we can go over the questions. Thank you.
I'm unmuted. All right, thank you very much, Patricia. Now we can move on to the questions. I've been trying to answer some of them, but it takes a while actually. It's much faster when talking. So since I already answered some of them, I will go, first to the Q&A. We have also in the chat some more questions, which is a little bit confusing, but let's go with the Q&A first. There's a question from anonymous attendee where the comparison, we did a comparison with moving the EV charging to align with maximum solar output to address minimum demand issues. Minimum demand issue is an issue for AIMO, not for the distribution companies. And this project is focused on the distribution companies. So yeah, no, we are not assessing that. Now, if AIMO wants to give us some money to do some research, yeah, we're not happy to receive that. And we can do the analysis. Now, what are the impacts of moving EV charging to the night, like at midnight? That's a great question that actually from the perspective of the distribution networks, again, they are used to have very little demand. Having a little bit more demand actually doesn't create any problem at all. If anything, actually would be very valuable as well for the whole system, because during minimum demand times, we're going to have a much more capacity behavior of the distribution networks, which also affects the voltages in the transmission network and IMO. So actually having these EVs at night, throughout the night, will make things better, assuming that things were not that great, of course. But if they're okay, they're going to remain okay. Now, moving on, Hassan is asking if it's possible to use recycling connection times of charging points that may reduce anxiety of customers. If I was to use recycling the connection times of charging points that may reduce anxiety. Well, yeah, I'm not understanding really the question here, Hassan. In this case, the charging times that we are using and the charging profiles are all derived from this project, this trial actually, and actual data that happened in the UK is called Electric Nation, as I was answering some of the questions. But that means that this is the actual behavior of EV users that is being reflected in this project. So I'm not entirely sure your question, but please feel free to send me an email just to go a little bit deeper. Graham is asking that if there's no notable differences between the results of local studies and what's being observed overseas where uptake of EVs is advanced. Well, it's the same. Lots of EVs create distribution network problems. That's it. So the big differences is how the networks have been designed. So here in Australia, we have our networks. If you remember one of my first slides, providing the ADMD, the after the reversing maximum demand, those values are relatively high compared to many countries in Europe. All right. In the UK, for instance, ADMD for houses, because they use a lot of gas for heating, there's no air conditioning there. So they use values of 1.5, 2 kilowatts. Here is double that, all right, or even more. So that means that for the UK, the impacts of electric vehicles will be seen much quicker in their local networks than here in Australia, all right. So that's the difference. But in terms of the nature of the problems, it's the same thing. In terms of the challenges, it's really the same thing. Now, where they're seeing the problem significantly or not, that depends on the uptake, and the uptake is not necessarily that big, unless we're talking about the Scandinavian countries, and that's another discussion. Gabriel Ko is asking, 80% figure of users not being affected with the connection is a good result. Yes, it is a good result, but it is just one network. We need to apply this to the other urban and rural networks that we have, and we might find different things, Gabriel. So it sounds very optimistic. I prefer just to be conservative and see what happens in the other cases. But we will provide those results for the other networks. Recordings available later? Yes, for sure. Andy is asking, was your study performed with real consumers or hypothetical based of meter data? Well, on the EV side, we have very realistic profiles, all the information in our previous report. As I mentioned, comes from Electric Nation data. But in terms of the demand of what happens at home, this has been based on smart meter data for the Victorian and the New South Wales networks, although it's Victorian smart meter data. So we agreed with the distribution companies that for New South Wales was okay as well. For task networks, we actually use some diversified profiles that they provided, because in task they have a different behavior of electricity consumption as well, because no access to gas necessarily for many customers. It means that they use electricity for heating purposes. So it's slightly different. So it's as realistic as it gets, if you want. Mohammed is asking two questions, okay? First one, disconnection schemes. Yes, time-based disconnection schemes, yes. How normally setting a lower voltage due to bring in from the feeder line should disconnection. So time-based disconnection is a simple solution, all right? It's a simple solution, but that doesn't necessarily mean that you are gonna always make sure that the network is okay. So that's the problem with time disconnection. If you know for sure that the problems always happen between 8 p.m. to 10 p.m. I'm just, giving just a number, then of course that would be fantastic. But then if everything is moved to 10 p.m. to midnight, you're not solving the problem. So you need to constantly check what the problem is. And that's the problem with just time-based solutions. The second question from Mohammed is second peak between 12 p.m. and 12 a.m. Yes, it's not being shifted, but demand increases along with it might take analysis in the future. Yes, absolutely right. You're absolutely right. Well spotted. So yes, as EV demand increases, we're creating a slightly higher demand in other times that we didn't used to have. But that is not necessarily to the extent that it's creating significant problems. And that's great. But of course, if we're really looking at massive penetrations, perhaps it's something to look at, but still the EV management strategy that we were presenting today was catering for any issues that can happen throughout the day anyways.
And also on that question, that second peak, I believe is largely driven by non-residential demand, which came from the SCADA data. It's sort of a quirk of that feeder. So the management, you see that peak chopped for the earlier peak because that's in the mostly residential feeders where they're overloading. That second peak is occurring in those mostly non-residential feeders, and it's not causing issues mostly in the LV feeders. So we don't see it chopped, but it could cause HV. If it does cause HV feed issues, that's another question.
Thanks, Will. There's a question from an anonymous attendee. Well, where future energy generation coming mostly from solar or wind, wouldn't pushing charging to after dark hours resulting higher tariff in the future? Well, I don't know. That's a big question. So why you have a future this is fully renewables, right? So what is the implication of this? Well, if the cost of energy is super cheap, that's one thing, all right? That sounds great. So it means that you can have more electricity. But we need to differentiate energy from power, guys, right? When we look at networks, it doesn't matter energy. It's all about power. It's about that moment in time where all your solar photovoltaic is generating and affecting the voltages and the assets, your conductors, your transformers, or the demand of electric vehicles. That again, because we're exceeding the normal levels of demand, so all your currents are much higher, all your voltages are much lower. So we need to focus on power when we talk about impacts on networks. Now, if we are looking at the system and prices, yes, that's another discussion, but we are really not dealing with that. So it doesn't matter where we have more solar or wind, the networks are a bottleneck that we need to deal with. And there are ways of dealing with this, just injecting more copper on the ground or doing something a little bit clever, all right? And that's what we're trying to show here. James, David, let me know, once we need to close shop. So I'm gonna answer just a couple of questions more, perhaps. Asif is asking, have you considered AMI to implement EV management strategy? Well, so it could be, if we are looking at the smart meters as a hub that can transfer information, yes, it can be that. It all depends on the reality of each distribution company. Some distribution companies can have smart meters and then they will be the hub to talk to the charging point, or they will need to put another device. Now, this is assuming that it's a distribution company managing the smart meters as well. What happens if actually the distribution company doesn't want to do this EV management strategy itself and prefers a third-party company to do it on their behalf somehow? Well, that's an option as well, all right? So there are different ways of implementing this. Simone is asking, Will, this is for you.
I'm asked, how did you implement the EV management scheme? What simulation environment, what area? So the power flow simulations are done on OpenDSS. So The different distribution companies had their HV feeders modeled in different software. That was all translated to OpenDSS and then built with the pseudo LV feeders on top of that. And then in terms of driving the power flow and the management and all of that stuff is all done in Python. So sort of interacting between Python and OpenDSS for every time step.
Thank you for that, Will. Question from Quentin, bidirectional charge solution. So we're talking about V2G, vehicle to grid. We are not investigating vehicle to grid at this stage. It is a reality. There are brands, manufacturers that are actually really providing that functionality, charging points, of course, as well. That is a reality that will happen in the future, but where it is something that will be used to deal with network, the local network, distribution network problems, that's another story. It is likely, my gut feeling, that will be used mostly to provide services for the likes of AIMO, unless we start seeing a provision of services locally as well, which can happen in the future. Question from Jack, could the distribution network operator implement price signaling? Yes, actually, well, not necessarily the distribution company, but the distribution company passing those signals as well to the corresponding suppliers, all right? So it depends on the reality in the world that you are, right? But yeah, bottom line, can we actually implement price signaling? Yes, actually, it is possible to do that, particularly if you have smart meters, like in Victoria, for instance. That's super easy. We already have time of use tariff. Not that it creates massive changes in behavior, but we have time of use tariff. But can we implement really a price that is so significant, perhaps, that some people really will change their behavior? Yes, that's correct. And we are going to investigate that, Jack, in the next month and a half that we have in this part of the project. So that's the time of use tariff that will be coming in the final report of this part of the study, and we will be sharing those results with you all. And I think that that's more or less where I need to stop. James, David?
Hello, Nando. Thank you. Thank you to yourself and Will and Patricia. That has been great. As always, there's many more questions than we have time to answer. But I suppose there's the slides from this, the video from this will be available. People can also catch up on the other reports and things that are available. And as you said, there'll be a follow-up output in a few months as you wrap up. This is only the initial findings. There'll be more information coming. So great to have people really keen. Yeah, I suppose, thank you very much. And we look forward to seeing everyone join us for the next one. So thanks, everyone. Thanks, James. Thanks, everyone else. So.
Thank you very much. And thank you for the question. We'll try to answer them somehow back to you. Thank you.
Thank you.
Thanks for attending, guys. Thank you.